All right, let's get into it. Today, we are going to unpack a really cool idea using something simple, a catapult, to understand the two big ways that change happens in, well, pretty much any system you can think of.
But let's kick things off with a question. I'm sure you've bumped into this yourself. You know, whether you're trying to bake the perfect sourdough loaf, shoot a free throw, or even just run a process at work. Why is it that even when you do everything the exact same way every time, the result is never perfectly identical? What gives? So to get to the bottom of this, let's picture a little experiment. We've got a catapult, right? And we're going to launch a little plastic ball 25 times in a row. Now, we're being super careful here. We've locked down the angle, the tension, the ball itself. Every single thing we can control is set to be identical for every single launch. But here is the puzzle. When we go and measure where each of those 25 balls landed, not a single one is in the exact same spot. They're all over the place. But, and this is the fascinating part, it's not total chaos. The landing spots, yeah, they're different, but they all fall within a surprisingly stable and predictable range. So the question is still, why? Well, luckily for us, a physicist and statistician by the name of Walter Shewhart was obsessed with this exact same puzzle way back in the 1930s. And the solution he came up with? It was absolutely revolutionary. So here was Shewhart's big aha moment. He realized that not all variation is created equal. He said that any variation you see in any process, from our little catapult to a massive factory floor, comes from one of two completely different kinds of causes. And he gave them names, common causes and special causes. Honestly, understanding the difference between these two is the master key to unlocking our catapult puzzle, and, well, a whole lot more. So let's break them down. So first up, we've got common causes. And the absolute best way to think about these is to imagine them as the constant, unavoidable background noise of any system. It's just always there. So common causes are all those zillions of little factors that are always a part of the process. For a catapult, we're talking about a tiny puff of wind, the ball being a millimeter to the left, the way it happens to rotate in the air, or even the microscopic differences in the force the operator uses each time. It's countless little things. Now, you'd think that all those countless little variables would just create complete chaos, right? But here's the mind-bending part Shewhart figured out. The combined effect of all this background noise, it actually averages out to create a consistent, stable, and, believe it or not, predictable amount of variation. And that brings us to a really key idea, what's called a stable process. See, when a system is only being affected by these common causes, its performance will naturally bounce around inside a predictable range. And we can actually calculate that range and draw it as upper and lower control limits. All of our normal catapult shots are going to land somewhere between those two lines. So let's lock that definition in. In Shewhart's world, all that natural variation happening inside those control limits, it has a name. We just call it noise. It's the expected, natural hum of the system doing its thing. Okay, but what happens when something falls outside of those lines? Well, that's where our second type of cause comes in. This isn't noise anymore. This is a signal. See, a special cause is totally different. It's some new factor that wasn't part of the system before. It's an unexpected event. Let's go back to our catapult operator. Imagine that on the fourth launch, their phone buzzes. They get distracted for a split second, and oops, they accidentally put the ball in a totally different spot on the catapult arm. That single one-off mistake, yep, that's a special cause. And bam! Look at the chart. You can see the result clear as day. That single error makes that fourth launch land way outside the normal, predictable control limits of the process. It sticks out like a sore thumb. And as Shewhart would tell us, this is not noise, this is a signal. It's your process yelling at you, saying, hey, something unusual happened right here. And that is the one point you should investigate, because unlike all the background noise, you can probably find one specific, assignable reason for it. So let's zoom out and put this all together. What Shewhart's framework really gives us is this powerful new lens to see the world as a tale of two very different kinds of processes. On one hand, you have the stable process. This is a system where the only things causing variation are those common causes, just the background noise. And because of that, the process is predictable. You have a pretty good idea that future results are going to land inside those control limits. But on the other hand, you have the unstable process. Now, this one's getting hit by both the regular background noise and these out-of-the-blue special cause signals. The result? Total chaos. The process is unpredictable. You can't draw stable control limits because you have no idea when the next special cause is going to come along and throw everything for a loop. And this table just lays it all out perfectly. A stable process? Predictable. It's only got common causes, so you can calculate its limits. It's pure background noise. An unstable process? Unpredictable. It's getting hit by common and special causes, so its limits are all over the place. It's a messy mix of noise and jarring signals. So what's the big takeaway here? The truly crucial point is this. Walter Shewhart's incredible gift to us wasn't just pointing out that there are two causes of variation. No. He gave us a statistical method to actually tell them apart. He gave us a way to scientifically separate the meaningless, random chatter from the truly meaningful message, a way to finally distinguish the noise from the signal. And that leaves us with one last massive question, doesn't it? Now that we actually have a way to tell the difference between the normal, everyday static of a system and a real, genuine signal that something important has changed, what do we do with that information? How do we use it? Now that is a story for another time.